elementary version of Calculus, Chapter 6, Section 2, Volumes of Cross-Sections. I'm your host, Dr. D. Okay, here we go. Now, we've talked about volumes created by taking a two-dimensional graph and rotating it around a horizontal or a vertical axis and getting a solid. Now, we're going to accomplish the solid by cross-sections over a particular two-dimensional base. So, let me show you what that looks like. All right, now, here's our base. It's a circle with radius r. And what we're going to do is we're going to put cross-sections of squares over this circle perpendicular to the x-axis that stick out from the board. Now, notice a square is going to have a length of a side. Now, the length of the side is going to determine, or is going to be determined by the distance from end to end of it. So the square right here in the center is going to be the largest square, so it's going to stick out from the board the same distance as 2 radii, and then the square, as you get down toward the end, is going to stick out from the board less. So it's going to make an interesting shaped solid. So here's basically what it's going to look like. These are our squares that are sticking straight out of the board. And since they're sticking straight out, you really can't see their height. So in order to look at their height, we're going to drop the x-axis flat, or drop the y-axis flat, and now you're going to see that our squares are going to stick up from our circle. So here is a sample of squares. Here's 4 of them. So you see the lightest color is in the back, and it's the largest square. And as you get your squares closer and closer to the edge, they get smaller and smaller. So now, what we're going to do then is show the sweeping of the squares. See, the squares get bigger and bigger and bigger until they get to the very center, and then when they get to the center, they start to get smaller and smaller and smaller till they get to the other edge where the last one would be 0. Okay. Now, here's what the solid would look like. It's basically a circular base with squares getting, so you can see here, now the squares are being swept through our solid. So this is called volume of cross-sections. This is different from volumes of rotation. And it also has a different way of calculating the volume. Notice the volume of the cylinder is going to be the area of the base times the height. Well, the volume of this thing is going to be the area of whatever the geometric shape is, in this case it's a square, times the thickness of each square. So it's the integral from negative r to r of the area dx. And the area is going to be given in terms of the base that you have. So let's try an example and you'll see what I'm saying. Okay. So I'm going to start with a simpler base. See, we had the base of a circle. Here's this base. What we want is the volume of the solid with base y equals negative x squared plus 1 from negative 1 to 1 with square cross sections perpendicular to the x-axis. Now, once again, I want you to draw this. So this is going to look like okay, here's 1, 1, negative 1, 1. Okay, so now we have our parabola. That's negative x squared plus 1. It's a parabola opening downward with vertex 0, 1, and it's going to have x-intercepts negative 1 and 1. Now, our squares are perpendicular to the x-axis. So our squares go like this. Now, what is the area of our squares? Well, the area is going to equal side times side. Well, what's the length of each side? It's going to be the distance from the x-axis up to the function, which is going to be negative x squared plus 1. So that's the length of one side. The area is going to be this amount squared. And the volume is simply the integral from a to b of the area as a function of x dx. Why? Because it's the area times the thickness of each square here. How thick is each square? Dx thick. So in our case then, the volume is going to equal the integral from negative 1 to 1 of this area, which is negative x squared plus 1 quantity squared. That's the area of each square times the thickness of each square. Now, we need to take advantage of the symmetry here, and notice the left and the right side of the y-axis are equal area. So that means instead of going from negative 1 to 1, I just want to go from 0 to 1 and double it. Now, I'm going to expand this to make it easier to integrate. So x squared squared is x to the 4th minus 2x squared plus 1 dx. So this can equal 2 times, integrate this, it's x to the 5th over 5, minus 2x cubed over 3, plus x from 0 to 1. So that means I can just put a 1 in here. So my volume equals 2 times 1/5 minus 2/3 plus 1. So this equals 2. Now, negative 2/3 plus 1 is 1/3, so it's 2 times 1/5 plus 1/3. So this is 2 times 3/15 plus 5/15. So this is 2 times 8/15. So my volume equals 16/15. Notice this does not have pi in it because it's not a volume of rotation. Each square is a length times a width, or side times side. So there's my volume, 16/15 cubic units. So notice, it's just the integral of the area as a function of x. So this really is fairly simple. All right, let's try the one, we'll try a different base now. So what we've got, yeah, we'll just do the next slide. Okay. So we want the volume of, let's see, how do we say this? A solid with circular base radius 1 with equilateral. Now, you know what? Before we do equilateral, let's do right triangles. So we'll do isosceles with isosceles right triangles perpendicular to the x-axis. Now, if you want to see what that actually looks like, oh, incidentally, if you want to see what this actually looks like, then that's going to be the pink ceiling decoration that's very first on the list. It was Alec Holt's project. Now, if you want to see what this looks like, this is Deborah Nash's project in red, white, and blue. So now let's do this thing. So we have circular base of radius 1. So that means, nice. There's my circular base. Okay, we've got to clean that up just a little. No, we don't. Okay. Now, our triangles are going to be isosceles right triangles perpendicular to the x-axis. So let's look at a single triangle. Now, the circle, the equation of a circle radius 1, you remember from math analysis, is x squared plus y squared equals 1. Now, if we want this as y is a function of x, then we say y squared equals 1 minus x squared. And that means y equals the square root of 1 minus x squared. All right, so that's a y value as a function of x. Now, if I would lay this triangle down, then I have a y value from here to here, and a y value from here to here. So in other words, the base of each rectangle is going to be 2y. And these are isosceles right triangles, so the height is 2y. So the area then equals 2y, or I should say 1/2 base times height. So the area equals 2y squared. When y is the square root of 1 minus x squared, so that makes area equal to 2 times the square root squared, makes it just 2 times 1 minus x squared. That's my area in terms of x. Now my volume is just the integral from left to right, -1 to 1, of the area times dx. So what we've said is the amount of solid we have here is basically the area times the thickness. So I take the area of every triangle times the thickness of each triangle. The thickness of each triangle is dx. There's my area. Bam, that's it, game over. This is a piece of cake now. And like we did before, I don't want to go -1 to 1 when I can just go 0 to 1. And so I'm going to make this 2 times this. So I'm going to make it 4 times the integral from 0 to 1 of 1 minus x squared dx. And then this becomes 4 times, we integrate, so we get x minus x cubed over 3 from 0 to 1. And so our volume then is 4 times 1 minus 1/3, which is 4 times 2/3, which is 8/3. That's it, game over. Okay, now let's crank up the juice just a bit. And we're going to do the exact same thing, only we're going to make our triangle equilateral. Equilateral? Okay, let's try that. So, if the triangles are equilateral, I'm just going to leave everything that we are going to use over here. Okay. Equilateral triangles. Okay, volume is circular base with radius 1 with equilateral triangles perpendicular to the x-axis. Now, if you want to see what this looks like up on the ceiling, that is Calc McGinnis. It's the, oh, and also Gerald Froelich did the same thing. So Gerald Froelich is in gold and Calc McGinnis is in blue and white stars. So we've got our same y equals square root of 1 minus x squared, but now each triangle is an equilateral triangle. Oh, nice. All right, we'll go with that. We're going with that. Okay, so that means it's going to be 2y across from here to here, because it's 1y up there, 1y down there. So 2y is across here. But if I take an equilateral right triangle and I split it down the middle, so I know this is a 60-degree angle, that's a 60. When I split that, that's 2 30s. So this becomes a 30, 60, 90. So with a 30, 60, 90, I know that this is y, and what's the altitude of a 30, 60, 90? Well, it's the square root of 3 times the short side. So this becomes square root of 3y, and now my area, we'll just stick with blue. So area equals 1/2 base times height. So 1/2 times base times height. All right, 1/2 base times height is the area. So this equals 1/2 times 2 is just 1. So we've got square root of 3y squared. Now what's y? The square root of 1 minus x squared. So that means the area equals the square root of 3 times 1 minus x squared. Really similar to what we just did. Now the volume then is just the integral from -1 to 1 of the area times the thickness of each triangle. And so we, once again, make this 2 times the integral from 0 to 1 of 1 minus x squared. And then do the integration, so it's 2 square root of 3 times x minus x cubed over 3 from 0 to 1. And now this becomes 1 minus 1/3, which is 2/3. So we've got the volume equals 2 square root of 3 times 2/3, which equals 4 square root of 3 over 3. Bam! That's it. So, get good at this, mainly for one reason. It's on the AP exam! Okay, that's it. Have fun with these.